So thanks for clicking my video again. I think at this stage I have already 153 views in total in my channel. So I'm well becoming a YouTube star soon. So I really appreciate your patience with me. So among my route to YouTube stardom, I will be, while waiting, I will be speaking and lecturing to you regarding wavefront-splitting interferometers. So I will be introducing to you basically what are optical instruments known as interferometers in this lecture, and I will introduce to you the main concepts that we need to know to understand how they behave. And I will classify interferometers quite arbitrarily, but I think this helps our treatment in the course. So I will divide interferometers into two classes, so namely the wavefront and amplitude splitting interferometers. And of course, in this lecture, I will be considering wavefront splitting interferometers. So essentially, I will do that by studying a historically quite known example of Young's double slit experiment. So this is what I will be doing, and I will be showing you the math. How do we calculate a kind of phase accumulation during that experiment? And then how do we see what kind of conditions we have for interference to take place in that experiment? So the instruments that they are based on interference are smartly named interferometers. And this is an arbitrary separation or division of different type between different types of interferometers. But let's do it because pedantically it makes sense, especially in the framework of our course. So I will just broadly say that there are wavefront splitting interferometers, and I will be considering them here in this lecture. And a second possibility, what kind of configuration we could have, is that we could have so-called amplitude splitting interferometers, and those will be considered later. And even though this division between different types of interferometers is maybe somewhat arbitrary, it helps our treatment. So I hope you also appreciate the time and effort we made in trying to prepare you the materials. And these wavefront splitting interferometers, essentially they are based on a configuration when we have fields from the same wavefront, and these fields interfere with each other. So essentially, schematically, things look like this. So we have a source, and then we have the observation point in which we're looking, do we have interference or not? And depending on the different optical path length difference, so between the difference between the paths of S1 and S2, we either have a constructive interference or destructive interference. And in what follows, we entirely neglect the possibility that our source and the light distributions we're considering would not be temporally coherent. So we implicitly assume here in what follows that we have perfectly temporally coherent light source, and that's it. But of course, since I hope you were listening my previous lecture, thanks so much for clicking and subscribing to the channel, is that we are kind of implicitly assuming that the separation between the path lengths is smaller than the coherence length, so that we have nice coherence properties between the two fields that are interfering. But nevertheless, this is the configuration that we are considering now. So we have two fields of the same phase front, and we are letting them to interfere with each other. And a good example, and perhaps the most known example, is the Young's double slit experiment. So we essentially have a light distribution, and we have two slits, and we're interested, and of course we have the wavefront that is coming into the two slits, and we are now interested in calculating what is the optical path difference for the field when it's propagating a distance of S1 from the first slit into the observation point located here at the point P, and then we have the observation, the propagation from the second slit's point, and then we have the optical path length S2 when we are looking the distance from the location of the second slit into the observation point P. So this is the configuration we are looking at, and here, of course, we want to calculate the phase difference that gives us a condition for the constructive versus destructive interference. And in a historical Young's double slit experiment, if you remember how it looked like, there actually were two slits. I think I will have a picture shortly appearing. And the first slit essentially is just meant to improve the spatial coherence of light. So already at that time, people knew that what is a spatial coherence, and they knew how they can improve the coherence properties of even just normal like light distributions, for example, the coherence of a sunlight. And let's now look how we can understand things, so how we can calculate the optical path lengths of S1 and S2 and how they are interfering on a screen at the point P. So essentially we could imagine that we have a camera cell there, a distance S away from the slit, and we can use that to record our interference pattern. So essentially this is the picture that I was waiting for. So in an original Young's double slit experiment, we actually had 2 slits. So first we had just a single slit, and what this helped was that we were getting, this was essentially sunlight that is not very coherent light distribution, and we were improving the coherence properties of sunlight by just introducing a slit. And then now essentially it's a small slit, so what goes through more or less just seems to be a spherical wave, and that has way better spatial coherence properties than just normal sunlight that consists of many modes propagating slightly in different locations into the location here. And now we have the double slit, and this is the main configuration of interest in this lecture, so that we are wanting to calculate how much of phase accumulation takes place for the field propagating from here into the observation point, and then we want to calculate and distinguish how much of optical path lengths the field propagates when it's coming from the second slit into the same observation point. And here we are assuming that we are placing this guy symmetrically, so that the kind of original phase front here is essentially identical, and only the kind of phase difference that matters is the difference between the optical path lengths of S1 and S2. So here the parameters of interest, say separation between the slits, in the first top picture we denote that as an A parameter, and in our case the distance in the or the distance of the observation point P from the optical axis is Y, and we are assuming that this is way smaller than the separation between the 2 slits and the screen. So essentially this is the S is the length between the or distance between the slits and the screen. And since we are looking at a far field configuration, essentially the theta, the angle between defined here, this is actually small, and arising from the fact that Y is small, S is large, so that then we can actually equate that this is actually very small. And now R1, that is essentially the optical path length coming from S1 point into the observation point P, and then the R2 is essentially the length from point S2 into the observation point P. And now we have defined the geometry, and we can actually start calculating by approximation. So the optical path differences that we want to calculate, that's approximately, so this R1 minus R2 is approximately S2 times B. So essentially this is what we are wanting to calculate. So we have B here. So we are assuming that the optical path length here into here is essentially the same as from here to here. So the only thing that we must consider is this path length here from point S2 into B. And this is essentially A times sine of theta. And when the angle is small, we can just equate that this is approximately A times theta. And this, in addition to looking at the geometry, leads to a condition that theta is approximately Y over S. So we're essentially looking at the configuration, and then we are like equating the angle into here, into this side, and then we see that this is essentially Y times S. So essentially the tangent of theta, that's by definition Y over S, and now the sine theta is divided by the tangent of theta is defined by sine of theta divided by cosine of theta. And now if you have a small angle, this is essentially sine of theta, and this is approximately the theta, and this gives me this equation here. So the phase difference, the delta, we can now just simply calculate. So delta is the amplitude of the wave vector k times the difference between R1 and R2. So this is how much of phase is being changed during propagation of light. And then this is the k, of course, is 2 pi divided by lambda. So we're implicitly assuming that we are in air. And then we have the phase difference arising from the difference between the R1 and R2. And this is, we have just calculated what that is. So it's A divided by S times Y. And now we know that when this phase difference is a multiple of 2 pi, so essentially when delta equals 2 pi times m, where m is an integer, then this, of course, gives us that this takes place when the r minus r2 equals m times lambda. And now m is an integer, and this is known as the interference order. So depending on what is the order of interference, we have a constructive interference. And this is a condition that tells us roughly that at what wavelengths we will start seeing constructive interference. And we are changing the integers, and we see that we have constructive interference at different wavelengths. So the mth maximum of the interference pattern, we can see that when ym is equal to m times s per a times lambda. And of course, we can write this in terms of the angle theta. So simply we can write it theta m, the theta m angle related to a mth interference order is simply m times lambda per a. And this is everything we need to know about the interference of a Young's double slit for now. Essentially, we are putting a camera into the screen, and we are recording an interference pattern. And when we have an mth interference order, when this equation is valid, then we see actually constructive interference. So we see irradiance associated with the given angle here. And then when we are changing the order of interference, or we are changing the properties of the slit, so essentially the distance between the slit A, or we are changing the incident wavelength, we are seeing the thetas being changing. And this is what essentially is how a Young's double slit works. So I'm now done with the second lecture of chapter 8. And next lecture, I will be speaking about amplitude splitting interferometers, so basically a thin film structures. So bear with me for a while, and please click on the new video, so that I will then have 154 views in total in my channel. Thanks for listening, and bye bye.